Hello everyone, we are from Group 8 and our presentation topic is Support Vector Machine. My name is Sapna Parekh and these are my group members. In upcoming slides, we will be covering the following topics. Let's start with what is a support vector machine? Support vector machine is the process of finding a hyperplane in an n-dimensional space that distinctly classifies the data points. Here we can see this red line, how this line classifies the two different data sets. Characteristics of SVM. Since the learning problem is formulated as a convex optimization problem, efficient algorithms are available to find the global minima of the objective function. Overfitting is addressed by maximizing the margin of the decision boundary, but the user will need to provide the type of kernel function and cost function. Difficult to handle missing values, robust to noise, high computational complexity for building the model.
Hello everyone, I am Narendra Paucha. I will be discussing about hyperplane and n-dimensional space and linear SVM. So hyperplanes are decision boundaries to help classify the data points into classes. So many hyperplanes that could be chosen, but we need to find the maximum margin so that the future data points could be classified with more confidence. So here in this example, we can see this is the best hyperplane and this is not as good. So hyper dimensions of hyperplane depend on the number of the features we have to classify. For example, if the number of input features is 2, the hyperplane can be just a single line. And if the number of input features is like 3, the hyperplane is the 2D plane. Linear SVM is the fast machine learning algorithm for solving multi-class classification problem for ultra-large dataset. So which implements a cutting plane algorithm for designing a linear support vector machine. Um, so linear SVM is linearly scalable routine. That means it creates a SVM model in a CPU time which scales linearly with the size of the training data set. So here in this example, we can see the decision boundary which classifies our training data set. Features of linear SVM. So efficiency in dealing with extra large data sets, say in the size of several million training data pairs, can be achieved with linear SVM. So and solving multi-class classification problem with n number of classes, working with high dimensional data in both sparse and dense format. And for linear SVM, we don't need any expensive computing resources, and because the processing time is for a linear SVM is linear with the data set. And linear SVM is ideal for contemporary application in digital advertisement, e-commerce, bioinformatics, proteomics, and banking service.
Hello, this is Ankit Pandita. I'll be going through linear support vector machine model and how it is trained. So the main task that is involved in training of SVM is estimating the parameters W and B so that we can determine the decision boundary in our data set. So let's take the population of a city as our training data, and let's say circles represent the not obese population and squares represent the obese population. Let's introduce a decision boundary or a threshold somewhere around this dotted line. And let's say if we have introduced a new data point somewhere around here in this case, uh, its mass is somewhat more than the threshold, so it will be classified as obese. But as we can clearly see, a point somewhere around here is much closer to non-obese data set than it is to the obese data set. So it should ideally be considered as not obese. That's why this kind of threshold does not make any sense. To avoid this, we take the edges of two data sets and we make a threshold right in the middle of those two data points. In this case, this square represents the edge of the obese population, and this circle represents the edge of non-obese population. Uh, so the threshold wx plus b equal to 0 is introduced right in the middle of these 2 points. The shortest distance between the threshold and the observation is known as margin. In this case, the distance from this threshold to this square and the distance from this threshold to this circle both represent as margin. In order to achieve largest margin, the threshold introduced should be right in the middle of these 2 points. So let's say if the threshold was somewhere closer to this circle, the margin will get smaller, and also if this threshold gets closer to this square, the margin will again get smaller. So when we introduce a threshold or a decision boundary that gives us the largest margin to make classification, that kind of that kind of threshold is known as maximal margin classifier.
Hello everyone, this is Siddharth Panda and I'll be explaining the linear SVM example. So in this example, we have given 4 negative labeled data points and 4 positively labeled data points. So if you can see in class A, we have 1, 2 positive labeled data points, and in class B, we have 1, 0 and 0, 1 are both are positive, and 3, -1, 6, -1, 0, -1 and -0 are all negative data points. So first we need to plot these data points, and what we need to do is that we need to identify the nearest data points to both of these classes, class A and class B. So as we can see, we have plotted all the data points. This is 0, -1, this is 1, 0, this is 0, 1, this is 1, 0, and then we have plotted the remaining one. This is 6, 1 and 6, -1 here. So this is the graph that we have plotted, and our objective is to find a linear SVM which can classify the given data set. So we will go to the next slide. Yes. So if you can see from those those two classes, we have found out S1, S2, and S3. So these are 3 equations. And what we need to do is that we need to add bias. A bias is nothing but an dimension that we need to add. So we have added bias number, bias input as 1. We are considering 1 as a bias input. So this will be the third dimension. 1 is X, 0 is Y. So, and then we need to calculate, we need to form an equation. So we have, since we have 3 points, so we need 3 alpha. So alpha 1, alpha 2, and alpha 3. In this equation, we can see that, and this alpha 1, alpha 2, alpha 3, these will be required to calculate the weight vector. And if you see in the first equation, we have S1 as common in this. So alpha S1 tilde S1, then so this will be a dot product, and then alpha 2 S2 S1, alpha 3 S3 S1. And in if you see the similar trend in both the rest of the equation, we have S2 common here and we have S3 common here. So based on the value of S1 in the first equation, we need to equate it to the -1. And if we see in this, we can see that S1 is on the negative side. So we have equated it to -1. Since S2 is on the positive side, we have equated it to +1. And similarly for S3, we have equated this equation to +1. And after calculating this dot product and everything, we will be getting this as the final equation. And after solving the equation, we will get the value of S1, we get the value of alpha 1 as -3.5, alpha 2 as 0.75 and alpha 3 as 0.75. So, and after that, we need to calculate the weight vector. So, W tilde is the weight vector, and it's the summation of alpha I to S tilde I. And I is nothing but the number of nearest data points. And here we can see that we have three variables, alpha 1, alpha 2, alpha 3. So we will use like alpha 1 S1, then alpha 2 S2, and alpha 3 S3. So this is nothing but S1 tilde, and S1 tilde is similar to S1, but we have added a bias input as 1 here. So this is the equation, and after we solve the equation, we have 1, 0, and -2. So finally, remembering that our vectors are augmented with a bias, we can equate the last entry in W tilde as the hyperplane offset D and write the separating hyperplane equation. So hyperplane equation is this: y equals to wx plus b, and w is 1 0 and b is -2. So b is nothing but the bias. So since we have added bias in our original equation, we need to take it out, and if you can see, the weight vector is now 1 0 and b is -2. So if we see at the graph, the final graph that we made, we can see that this is 1 0 plane, and it is parallel to the y-axis, and it separates all the data points of both the classes into these are all the positive data points and these are all the negative data points. So that's how we can use linear SVM to classify.
Till now, we have seen about the linearly separable case of the SVM. Now we are going to look into the non-separable case, where data cannot be separated by a line or a boundary. SVM address non-separable cases by introducing two new concepts called as soft margin and kernel tricks. Let us consider an example. So this is the linearly separable case where we can draw a boundary between the data points. For suppose if we add one red dot on the opposite side of the boundary, we cannot make it as a linearly separable case. So to handle this, we have two solutions. One is soft margin. Now we are going to talk about the soft margin. Two types of misclassifications are tolerated by SVM under soft margin. The dot is on the wrong side of the decision boundary, but is on the correct side of the margin, shown here. The other one is the dot is on the wrong side of the decision boundary and on the wrong side of the margin, shown here. So we can see here the red dot is on the wrong side of the decision boundary. So applying soft margin, SVM tolerates a few dots to get misclassified and tries to balance between the trade-off between finding a line that maximizes the margin and minimizes the classification. We can achieve by using some constraint known as psi, where psi is called as the slack variable. Slack will be 0 for all the points that are on the correct side of the margin, and psi will be greater than 1 when the points are on the wrong side of the margin. So for here, the psi will be greater than 1 because it is on the wrong side of the margin, and here psi will be less than 1 because it is classified correctly but on the opposite side of the boundary.